Thank you again for joining us for our March Tech Talk. Today, I have the pleasure of welcoming Kevin Owen from Upat. Kevin is PR Eng, holds a BSc in Civil Engineering from Stellenbosch and from Wits and an MBA from Stellenbosch. He started his working career as a consulting engineer, but then swapped sides to work on the contracting side of things, where he spent the majority of his time. He's worked mostly on large infrastructure projects and industrial projects all over the world, from China, the Middle East, and throughout Africa. He's been involved with Upat for the last 12 years as their technical manager. And today he's going to talk to us about postfix anchoring technology with some case studies following that. It's a topic that I'm very happy to hear being spoken about, because I think there's a lot of misinterpretation of tabulated design information out there from a number of manufacturers, and we're good to hear somebody in the industry talk to us about how to go about properly and safely designing anchors. I'm also particularly interested to hear what Kevin has to say about the new SANS code that's coming out for concrete anchors, which is based on the Eurocode, I believe. So with that, I'm going to hand over to you, Kevin. Thank you very much. Kevin, do you want to unmute yourself and we can get started?
Okay. Are we good to go?
All yours. Thanks, Kevin.
Thank you very much. And thanks to everyone for attending. Thanks for the introduction, Chris. We're going to talk about the there we go. What types of anchors are available? A little bit about the code, and for everyone's interest, we at Upat collaborated with our opposition HILTI, and together with the input of Professor Peter Day, whom I'm sure most of you know, we've had the Eurocode adopted as part of the SANS code. So it is part of the SANS concrete code now, and I'm going to talk a little bit about that and how it works, and time permitting, we're going to go through a couple of case studies. So firstly, you have chemical anchors. Chemicals are normally used with threaded rod or reinforcing steel. And the point that I want to make here is that there are different types of chemical that are available, and each one has its own applications. Typically, it has two components: the mixer, the hardener, and the chemical. And the mixing nozzle is there to ensure that the components are mixed in the correct proportions. The embedment for chemical anchors is 10 to 20 times the diameter of the anchor. And that's because the full strength of the steel is developed within that embedment depth. And the reason for that is with chemicals, you are able to achieve much higher bond stresses between the chemical and the concrete than one normally uses in conventional reinforced concrete design. Okay, so you get different types of chemicals, and each one has its own characteristics and its own properties. A bonded anchor is an anchor that's set into concrete after the concrete has been poured, and basically you get capsule systems or injection systems, and that is broken down into either polyesters, vinyl esters, or epoxies. Those are the three different types of chemicals which all the major manufacturers use in order to manufacture their products. Epoxies are really the top of the range. Epoxies can be used where the hole has been cored. Epoxies can be used underwater. Epoxies take a long time to set, and typically an epoxy has a cube strength of around 120 MPa. one of the very well-known epoxies is the Hilti RE500, and the Fisher equivalent is the FIS-EM. Then you get vinyl esters, slightly lower in performing. Not all vinyl esters can be used in cored holes. Some of them can only be used in drilled holes. Some vinyl esters have cement in their hardener, so be careful if they cannot be used in wet holes. Curing time is much shorter than that of epoxies, and they have a cube strength of around 100 MPa. And then basically at the bottom of the ladder is polyester-based chemicals. Not recommended for structural applications. Polyesters are sensitive to moisture, and if they are continually exposed to moisture, they're going to eventually lose their strength. And we will see that in one of the case studies a bit later on. And the cube strength is around 60 MPa. So when one is using chemicals, you have to consider, has the hole been drilled or cored? Is it a wet or a dry hole? What are the curing times? What are the long-term temperature conditions? Has the hole been properly cleaned? People always go on about price. Polyester is the cheapest and the lowest performing. Epoxies are the most expensive and the highest performing. This is just a graph to show what bond stresses can be achieved with the different cleaning methods. So the red curves there show that's the very, very basic, the very minimum that the manufacturers recommend, a hand brush and a hand pump, which is basically a bicycle pump. You can get bond stresses of 4 or 5 MPa. Then if you go up with a cleaning effort, compressed air, machine-driven nylon brush, you can achieve higher bond stresses. And then compressed air, machine-driven wire brush gives you the best result. So really, all that boils down to is that the better the cleaning effort, the better the result you're going to get. Okay, installation of a chemical in concrete. This is a Fisher training video. It's just illustrated to show you what needs to be done. So the hole is drilled. It must be cleaned out. Blow, brush, blow is what all the manufacturers specify. And blow again. That's a typical dispenser gun. And one always has to give it about 2 or 3 squirts first before injecting in the hole to make sure that it's uniformly mixed. Typical rule of thumb is you fill the hole about 2/3 of its depth with a chemical and then turn the threaded rod in to get maximum surface area contact between the chemical and the stud. And curing time depends on temperature. And that is the installation of a chemical anchor. Then you get expansion anchors, and an expansion anchor comes from the old raw bolt. I'm sure everybody's familiar with the raw bolt, and these work on exactly the same principle. You have a wedge at the bottom end of the anchor with a clip, and as the anchor is tightened, that clip expands against the wedge and locks in the concrete. A big advantage over this type of product over the raw bolt, and I'm not knocking the raw bolt, but its technology has been superseded, is that you can take any one of these anchors, either an expansion anchor or a chemical anchor, put your base plate down on the concrete, drill through the holes into the base plate and fix the chemical through those holes, which you cannot do with a raw bolt. As everybody knows, with raw bolts, if you want to fix a base plate with raw bolts, you've got to mark the holes, remove the base plate, drill the holes, put the barrels down, then put the base back over those holes and hope that the holes line up and put the bolts in, which is very time consuming, and it leads to the top possibilities of error. Pound for pound, a chemical anchor has a higher load capacity than an expansion anchor of the same diameter. Well, let's say, for example, an M12, a chemical stud is 12 millimeters diameter all the way down through its full length. And take this, for example, an M12 expansion anchor. Over there, at that point where the clip fits around the anchor, the diameter is slightly smaller than 12. So a chain will always break at its weakest link. And at that point, you've got a diameter of less than the specified diameter of the anchor. And that's why the load capacity is slightly less than a comparative size chemical anchor. Okay, installation of an expansion anchor. There you can see what I was saying. You can basically drill through the base plate. Knock the anchor in and tighten it up. And you can see how the clip expands against the anchor at the back. An advantage of an expansion anchor over a chemical anchor is that expansion anchors can be loaded immediately. You don't have any curing times to worry about. Then you get what's called an undercut anchor. An undercut anchor is basically an under-reamed anchor where a conical shaped hole is made in the concrete and the anchor is then set into the concrete. Very high performance, but they are expensive because they need special tools in order to install them. So here is a video of the installation of an undercut anchor. And I'm showing this because you'll see what happens when at failure. So that's you can see there's a special drill bit that is needed. So the first thing they do is they drill the cylindrical hole. And now he's going to under-ream it. So by reaming it in that manner, that creates the conical shape of the hole. And that anchor has a sleeve which is knocked down and it opens up on the inside of the hole. But you can see you need that special setting tool. So the anchor is protruding, the sleeve has gone all the way down. And now it is being tested to failure. You can see this is a very old video by the type of computer that you're looking at. But the principles are still apply. So it has been loaded to the point where the concrete has failed. Now take note you can see how the sleeve is opened up on the inside And that is what we call the typical cone failure of the concrete. And cone failure is very prevalent, and it forms an important part of anchor design. There we go, that's the concrete cone. And that is actually, cone failure is actually a tensile failure of the concrete. Okay, then fairly new on the market is what they call self-tapping concrete screws. Quick and easy to install. They can be reused. And also because they can be removed, they're ideal for temporary structures, such as scaffolding and formwork. And they are becoming more and more popular. And the design principles are exactly the same. Whether you use a chemical anchor or an expansion anchor or self-tapping concrete screw, the principles remain exactly the same. Okay, so that's the code. The code comes from the Eurocode, and we, together with Hilti, and thanks to Professor Peter Day, got this accepted as part of the SANS code. And what this does is, when a group of anchors are acting together, there are 4 possible failure modes in tension and 3 possible failure modes in shear. And the design then checks the resisting load for each possible failure mode and looks at the decisive case, and it does the same for each possible shear failure mode, and then combine tension and shear, which your structures guys will know all about. So, if an anchor is in tension, the first possible failure mode is steel failure, direct failure of the steel, where the steel will fail in tension. That represents the upper limit on the load capacity of an anchor. You can get concrete cone failure, which we've seen, and the diameter of the cone is typically 3 times the embedment depth of the anchor. So this is now when the design principles start coming in. If an anchor is in tension and you have concrete cone failure, you can see that's the volume of concrete that is resisting that tension load. Now, when you start spacing anchors close to each other, you will see that there's a bit of an overlap. So what this design philosophy code does is it takes the load capacity of a single anchor, and then it makes a whole lot of adjustments according to the geometry and applies adjustment factors to the basic resisting load for a single anchor. So, for example, over here, you will see here's an anchor that's close to the edge of the concrete. So once again, that full cone cannot be developed. So the capacity of this will be the capacity of a single anchor in concrete multiplied by some resisting adjusting factor to reduce that capacity. Okay, then you can get pull out, pull through, which means that the anchor just pulls out. If you have an expansion anchor, normally that happens if the hole has not been drilled to the correct diameter, if the hole is too big. For expansion anchors, the diameter of the drill hole must be exactly the same as the diameter of the anchor. For chemical anchors, the diameter of the drill hole must be a couple of millimeters larger than the diameter of the stud or than the diameter of the rebar, because you want to have that chemical all the way around in that annulus between the hole and the stud. And then you can get concrete splitting. This happens typically with expansion anchors. If a big bunch of expansion anchors are too close to each other, they will create splitting. And also splitting is prevalent when the concrete section isn't that deep, if it's relatively thin. If you've got a big, deep block of concrete underneath these anchors, then the chances of splitting are reduced. So splitting happens typically in thin sections. Okay, in shear, you can get direct steel failure, where you've got a shear load, and that's what happens to the anchor. That's normally not the decisive case. Then you get pry out and edge failure. Pry out is a shear load when you have a shear load and that anchor pushes a wedge of concrete out behind it. And that's actually also a tensile failure of the concrete. And edge failure is where you have a shear load and there's just not enough concrete resisting that load, and you will get failure on the edge. So each one of those failure modes has to be considered, and the worst case is the one that's decisive, and always the resisting load must be greater than the applied load. Okay, here's just an example of pry out. So it's a big shear load being applied, and the concrete breaks out at the back. Okay, and here's an example of edge failure. This has been done with expansion anchors, very close to the edge of the concrete, and they are set quite close to each other. So they're spaced close to each other, and the edge distance is 55 millimeters. So that would be typically probably a 12 millimeter diameter anchor, and the drill hole must be 12 millimeters as well. You'll see all these expansion anchors have rounded heads to prevent the threads from being damaged whilst the anchor is being knocked in. And then what he's going to do here is just over tighten them. So that says that the installation torque for that product is 12 Newton meters. That's what he's trying to tell you. That's important. Every expansion anchor does have its own installation torque. And the problem that we find on sites is that not always do you see a torque wrench on site. So it's been tightened up, and that's actually causing expansion of the concrete. So that's going to almost 10 times more than the specified torque. And that is what happens. So I think that that has been made pretty clear what has happened there. Let us continue. Right. So, as I said, the resisting loads for every possible failure mode are calculated, and adjustment factors are applied. So for cone failure, this is an empirical formula that's been developed through lots and lots of trials, and the resisting load for concrete cone failure is K1, which is a factor depending on if the concrete is in tension or compression, multiplied by the square root of the cube strength times the effective depth to the 1.5. That is done for every failure mode, and that is how the resisting load is then calculated, plus all adjustment factors. Let's have a look and see what I mean. So you can see anchor spacing, if the circles of the two cones are just touching, then they don't have an effect on each other. But as the anchors get closer, you have an overlap of the cones. And what the code says is that an idealized concrete cone is the area of concrete that is required for the full cone to develop. And in this particular instance, that is the idealized area that we're talking about, which is just diameter times diameter. It's the area which is required for a full failure cone to develop. Now, when you have two anchors, what the calculation does, and I'm just showing you this because if you use our design software, the Fisher design software, or the Hilti design software, they're both based on the same code, you'll see this a lot, which is basically an adjustment factor. It's the actual area of the geometry of that configuration divided by the idealized area. That's all that is doing. But you'll see those calculations a lot if you use the software. Same with edge distance. That the adjustment factor is the actual area over the idealized area. And then you get exactly the same thing with shear loads. That is a diagram of an anchor in tension with the development of the cone. And if you apply a shear load, you get that same dispersion. And this is the volume of concrete that is resisting that shear load. Okay, so they do exactly the same thing with shear loads, where you get that would be the idealized area. That's a 35-degree angle. C1 is the edge distance, and that dimension is 3 times the edge distance. And the depth is 1.5 times the edge distance. Okay, so once again, then you'll see the adjustment factor, which is the actual area divided by the idealized area. And that's how the design works for all failure modes. Okay, so now we're going to do a couple of case studies. And the first one is at Orkney Water Treatment Works. Original water treatment works was constructed in the late 70s and upgraded in 2012. One part of the upgrade was to increase the height of the existing launders by about 2.5 meters to give more hydraulic capacity. Okay, the existing walls had to be strengthened to take the additional hydraulic head. And this was done by tie beams inside the launders, anchored onto the inside walls. So let's see what happened. All right, so that would be part of the existing wall. They were heightened by about 2.5 meters or so. So that would be a new wall. And inside the channels, you had these tie beams, which held the wall onto the existing structure. And how did that happen? You can see there the wall pulling away due to the hydraulic pressure. The pressure was, there was something wrong with the anchor, and the whole wall pulled away. Now, why did it pull away? This collapse took place, and of course the supplier, being Fisher, were called and were told that we supplied an inferior product, which is always the case when a failure of this nature takes place. They always go to the supplier and query the supplier. The contractor that did the work is one of our customers, and we then looked into the specification, and the specification said nothing other than tie beams must be fixed to the walls with a chemical anchor. That was it. No other description was given, no other specification was given. That was it. So what did the contractor do? As all contractors do, he went for the cheapest possible chemical that was available, which was polyester. And we went back on our records, and our sales records did show that at the time that this was done, we sold this contractor a lot of polyester chemical. And there was no advice that was sought by the contractor or by the consulting engineer. This guy came in and just said, give us X tubes of this polyester. And so no question was asked where it was to be used. And polyester, and this is what happened. Polyester is not permitted in a moist environment. Polyester is like soap. If it's exposed to moisture, it becomes soft and it weakens. It didn't fail overnight. The works were completed in 2012, and that collapse took place about 18 months later. We were called in to do this examination investigation in about July, August of 2013. So it took time for this to manifest itself. It didn't fail immediately, but it did fail, and partly because polyester was completely the incorrect chemical to be used in those conditions. The other reason that there was failure was because the insides of these walls were pretty much like a spider's leg. They weren't straight. They were wavy all over the place. And the contractor had one fixed length of tie beams. And so there were plenty of gaps in between the base plates and the surface of the concrete. And these irregularities were made up with a grout packing in between the base plates and the walls. There's nothing wrong with that, but the anchors that were purchased from us were all a fixed length. Now, the more grout that you pack in there, the less the anchor is embedded into the concrete. And the strength, the tensile strength of an anchor depends, especially a chemical anchor, it depends on its embedment into the concrete. And, there was up to 60 millimeters of grout. Now, that's fine. There's nothing wrong with that. But then the correct embedment depth should have been used. In other words, the contractor should have purchased anchors which were 60 millimeters longer than the ones that they used to take account of that up to 60 millimeters of grout. So really two causes of failure in this case study, and the one was the absolutely incorrect selection of chemical. Nothing was specified, so the contractor couldn't really be held to account for that. And then, of course, the anchors got to go in there to their correct embedment depth. I've just seen so many cases where there's clashes with rebar. So what does the contractor do? He just cuts the anchor so as to avoid clashing with the rebar, and that reduces the capability and the load capacity of the anchor. It's as simple as that. Yeah, incorrect anchor selection can lead to injuries or fatalities. Very lucky there was no injury or no fatality here. It happened on a Friday evening, and there weren't too many staff on the plant. But you can see, you know, that's a total of about 5 meters high concrete wall, and that whole thing collapsed. That could have resulted in fatalities. Lucky that nothing happened there in terms of that. Okay, another one, rugby grandstand at a school in the Western Cape. We were approached by a loss adjuster to give our opinion on what happened here. At the time that we were approached, there was a claim going on between the client and the consulting engineer and the contractor, a big fight going on. So we were asked, I asked if we could use this as a case study, and we were given permission to use this as a case study, but no names, no pectoral. So I don't even know, I just know that it took place in the Western Cape. I don't know the name of the school. I don't know the name of the contractor. And I don't know the name of the consulting engineer. But there we go. Failure of a rugby grandstand. It was caused by very high winds. The structure was under-designed, questionable anchor selection, and it looked like in some places the hole cleaning was insufficient and chemicals may not have been used to spec. The outcome of this case, in fact, which was resolved after I prepared these slides, was that the consultant actually paid for 80% of the cost of the remedial work, and the contractor paid for 20%. In my opinion, it could have been a bit more equally split, but that was the outcome. Not just one event, but a whole number of events that took place. So have a look at the photos. Now have a look at that. That is a screw bolt. You can see by the threads. And there is a slightly different anchor next to it. This looks like concrete cone failure, partial cone failure, but you can see how this steelwork is buckled. So in this case, it looks as if, you know, the anchor was okay, the concrete was okay, but the load was just too much. But two different types of anchors. The fact that the base plate was deformed indicates that it was overstressed, under-designed. Screw bolt on the right, chemical on the left. Also see the screw bolt is a little bit rusted, meaning maybe that the hole was a little bit, was drilled a little bit bigger than it should have been. Now, I want to point out, we'll see a few more examples of this, and I am watching the time, Chris. There is no code in the world anywhere that allows different types of anchors in the same group. Apparently, this contractor had some anchors left over from a previous contract, and it was agreed to mix and match these anchors, which there is no code that allows that. So, and there we go. Have a look at that. That's a screw bolt, and that is a chemical. There you can see some concrete cone failure. The fact that the chemical, that the anchor is pulled out with the chemical wrapped around the stud indicates to us, and we've seen this many times, that probably the hole wasn't properly cleaned. All right, again, different types of anchors in the same group of anchor, which is absolutely not permitted. Both anchors failed by pull-out, probably due to high loading. Okay, high loading. When you get that with a chemical, it also means that the hull may not have been properly cleaned. There you see it again. Different anchors in the same. That we don't know. That's not one of ours. That's not one of Hilty's. Who knows where that came from? Maybe that came from Builders Warehouse. Who knows? You do have steel failure. So in this case, that's overload, under design, because the anchor held and the steel actually failed. So the load was too high. The applied load was too high for that particular anchor. There you've got a cone failure. Example of cone failure. That means the capacity of the concrete was exceeded, meaning the loads were too high. When you have this, when you have the anchor, the chemical peeling off the anchor like that, it means that the chemical was probably not properly mixed. When it's brittle and you can break off the chemical like that, it means that the chemicals were not properly mixed. Also, you can see there's rust on these anchors, which also suggests the ingress of water, meaning probably that the holes weren't properly filled up and you got water going in. If a hole is properly filled with chemical, I said earlier on, the rule of thumb is the hole must be filled about 2/3, and then you insert the stud. And if there is sufficient chemical in that hole, the stud will displace the chemical to the point where the chemical is flush with the surface of the concrete. And that was clearly not the case over here. Okay, there, a packer plate was used, and the base plate sheared off completely at the weld. Who knows, maybe there was some questionable quality of welding as well. So the under design, you may not use different types of anchors in one connection. Who knows what anchors were used? Some holes were not properly cleaned. Not enough consideration from all parties for the consequences of failure. Right. This is just very quickly the risk of mixing different brands. Now, I've seen that on sites many times where a contractor will use a product from Fisher, and then he'll use a Hilty product, a Hilty equivalent. Now, that's very, very dangerous. Just don't allow that on site ever, because if there is a failure, both suppliers will just say, sorry, my friend, prove to us that it was the Fisher product that failed, or prove to us that it was the Hilty product that failed. And you will find that both suppliers will just step back and say, sorry, this is, it's just not on, and prove which one was which product failed. Because once an anchor is set into concrete, our products are made from polyester or vinyl ester or epoxies, and so are our opposition products. Once it's set in the concrete, and you have a failure, it's very difficult to pinpoint what brand it was. Be careful of over-the-counter purchases. You go to I've seen failures take place, and you ask the contractor, where did you buy these anchors from? Oh no, they came from Builders Warehouse, for example. Now, I am not knocking Builders Warehouse at all. Please don't get me wrong. But if you go and purchase an anchor from Builders Warehouse and you ask the salesman to give you a load chart for that particular product, he won't know what the devil you're talking about. And that's the risk of buying stuff from the hardware stores and from people that don't actually understand the purposes of these anchors. So be very, very careful about that. Okay, we're going to do one or two more case studies. I'll go through this fairly quickly. This was during the construction, the upgrade of the ROSEBANK Mall a couple of years ago, I think 2012, 2013. What happened was part of the shopping area was kept open, and then other parts were cordoned off to allow for construction. And temporary hoardings were placed in between the construction areas and the live shopping areas to separate the shopping area from the construction activities. There was collapse of a temporary hoarding, and that's what it looked like. That's the temporary hoarding. It consisted of drywalling and drywall columns, which were fixed to the floor at floor level, and actually fixed to a bulkhead, which formed part of the permanent suspended ceiling. And that for me was a mistake. To fix any temporary structure to a suspended ceiling. Fixing anything to a suspended ceiling is, to my mind, not such a smart idea. Those are the drywall channels. Look at that. All of these channels were joined in the same line, and that created a line of weakness and a pivot point. So that certainly is one of the contributing factors towards this failure. You know, if these joints had been staggered, you would have reduced the possibility of that happening. Okay, there it is again. There you can see all of these drywall channels were joined at the same point in the same line. And that was definitely a plane of weakness. Had the joints in the temporary columns been staggered, this might not have happened. Also not a good idea to fix the top of the hoarding to a ceiling bulkhead. Yeah, so the ceiling collapse, once again, we were called in because it was our fixings that were used to carry the suspended ceiling. And we did about 120 different load tests on the actual anchors used. And we got the ceiling supplier in, the ceiling contractor and the supplier. The supplier, the ceiling came from Saint-Gobain. I'm sure a lot of you know who Saint-Gobain is. We got the loads accurately calculated and did a lot of tests, and it certainly wasn't the anchor that failed. But probably the temporary hoarding was bumped, and it happened after hours. This pulled the bulkhead, and because you had that plane of weakness, the whole thing came down. Okay, and I've got time for one more case study, which is very, very interesting. Okay, so let's go to Nubia Business Park. This took place in Durban a couple of years ago. Conventional construction, concrete columns, concrete beams, concrete slabs with brick infill in between the columns, and the structural steel was set, steel trusses were set into the tops of the concrete columns. There was one heck of a wind which blew, which took place on a Thursday evening, and that just lifted the roof off. This was during the course of construction that this happened, and it just lifted most of the roof off completely. And you can see the damage. And once again, the anchors were specified as one of our products was specified to fix the steel trusses to the tops of the concrete columns. So we were called out to have a look, and this was one thing we saw: anchors cut on site to avoid rebar, reducing the embedment depth. And that chemical looks brittle, suggesting that the chemical wasn't properly mixed. There you can see it's been cut. That's not permitted. You got to take the anchor to their full depth. The chemical around the stud appears brittle, indicating insufficient mixing or insufficient cleaning. Okay. Columns raised to level with no splice bars. Have a look at that. for some reason, which I do not know, about 30% of the columns were not poured to their correct height. The steel fixing contractor pointed out to us that, you know, in some places these columns were raised just by putting a box around that concrete and filling it up with concrete with no splice bars, which is not a smart idea. And in other places, have a look at this. The columns were raised to their correct level with brickwork, and the brickwork was then plastered to make it look like concrete. And then the structural steel trusses were set using our products into the brickwork. No, that was pretty, you know, that's not good engineering at all. And it certainly wasn't product failure. So there we go. So it was very bad weather that lifted that roof off. Anchors were cut, and where the columns were not cast to the correct height, they were brought up to height using brickwork, and anchors were set in brickwork, and that has a couple of layers of brick have got no tensile capacity. There again, our products were found on site as well as Hilti products. This failure was not product failure, but once again, if that had been the case, it would have been very difficult to prove which was the guilty party and which was the guilty product that failed. Once again, both suppliers would have just stepped back and said, well, prove which one is it. So we're just about time. I'm not going to go any further. So to everybody there, you know, there's installing anchors is not rocket science. You know, you just got to make sure that the holes are properly cleaned and the chemical is properly mixed. Don't cut the chemical short, because then you're affecting the capacity of the anchor. And, you know, be very, very careful about using different brands on the same site, because you're just leading with the jaw there, honestly. So that will conclude my presentation. If there are any questions, please. And thanks very much once again for the opportunity to give you folks this presentation. Much appreciated, Chris. And thank you very much.